This is part 2 of Chapter 3 Summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. In this video I'm finishing Chapter 3 with the review of information theory as it pertains to deep learning. Information theory is a mathematical theory that provides a large set of tools for analyzing signals, which in particular is useful because in real life, signals or their measurements are often perturbed and as such cannot be interpreted as being 100% true or 100% useful information or input. Some of the most classical interpretations of information theory aren't as applicable in machine learning, but the classical interpretations relate to computing expected lengths of signal messages from probability distributions using encoding schemes. In machine learning, the tools from information theory are useful to distinguish between distributions. The big idea when it comes to information theory is that the degree to which some data is informative can be quantified. The thing is, we're not talking about bits and bytes and that sort of thing as they're understood in computer science. The underlying premise is that the information that an unlikely event has occurred is actually more informative than the knowledge that a likely event has occurred. Some principles of the idea are listed here. Here's an example. If I tell you the sun rose this morning, you might say, "Thanks, but you haven't told me anything." This kind of colloquial response encapsulates the idea of information theory, that since the sun rises and falls every morning, the event occurs with complete certainty, and so receiving that data point technically contains zero information. This would be as opposed to, for example, me telling you a large solar flare was released this morning. This statement would have information inherent to it. With respect to information additivity, the example is given that being told a coin toss came up heads twice yields twice as much information as being told one toss came up heads once. As you might expect from mathematical theory, there is a mathematical function which expresses this idea and fits these properties, which is presented here. The self-information of an event, where a random variable x takes on value x, is equal to the negative logarithm of the probability of the value being taken on. The units of the value returned by this function depends on the base from which the logarithm is taken. For the deep learning book, Euler's number is always used as the base. So in this case, if an event has probability of 1 over e, then the information of this event is 1 nat. Nat is the unit with the natural logarithm. You should note that this expression only refers to the self-information for a single outcome. As was discussed in the last video, the circumstances are slightly different for a continuous random variable. The same definition of information as seen here is used for continuous variables, but more as an analogy. Some of the properties don't apply though. For example, at a point where the continuous probability distribution function is equal to 1, that doesn't mean that that outcome is guaranteed to occur, and yet it would be computed to carry zero information. To deal with this, we employ the idea of Shannon entropy. The Shannon entropy of a distribution is the expected amount of information in an event drawn from that distribution. As such, it gives a lower bound, on average, for the number of units of data to encode in the event returned from the distribution. Again, note the units would depend on the base used. Roughly speaking, the information content of an event has an inverse relationship compared to the probability of the event. And so broad, wide probability distributions with high variance will have higher average information content, and tight probability distributions with low variance will typically have lower Shannon entropy, corresponding to the average information content. Shannon entropy applies to discrete and continuous variables alike, although it's known as differential entropy for continuous variables. This chart shows a plot of the Shannon entropy for a binary random variable, with the parameter of the distribution varying in the x-axis. So this would be a Bernoulli random variable. What you can see here is that entropy is at a minimum when outcomes are totally certain, for parameters 0 or 1. Conversely, entropy is at a maximum when the parameter is equal to 0.5. That could be understood as being the case, since when the parameter is 0.5, the distribution is most uncertain as it could be. If it was 0.6, for example, then you would know that in the long term you would have a tendency to return more ones than zeros. But as it's at 0.5, it's the most uncertain it could be. Moving on from this, The KULLBACK-LIEBLER or KL divergence is a concept used to measure how different two separate probability distributions of the same random variable are. The divergence value can be understood as the extra amount of information needed to send a message, containing symbols drawn from probability distribution P, if we use a code that was designed to minimize the lengths of messages drawn from probability distribution Q. It's really important to note that the KL divergence is a non-symmetrical measure. The measure is different depending on the order in which the two distributions in the function are taken, or input. This chart visually shows how the KL divergence is asymmetric. In the chart on the left, the green plot is the result of minimizing divergence with the variable distribution as the second argument. In the chart on the right, the green plot is again the result of trying to minimize divergence between the two distributions, except the plot that's changing, the distribution that's variable, is the first argument in the divergence equation. Either one of these solutions could be desirable. It depends on the application. In machine learning contexts, some applications require an approximation of a distribution that places high probability anywhere the distribution places high probability. This is the example on the left. In other applications, an approximation may be required which rarely places high probability anywhere that the distribution places low probability. This is the example on the right. You can think of these two cases as two sides of the same coin. For example, if you're asked how much ketchup do you want on your fries, you could answer positively by saying very much, or you could ask for the same thing by answering negatively, saying not very little. The choice reflects the prioritization for the application. So in the example on the left, the minimization blurs the multiple mode. The example on the right is representative of a scenario where there are multiple widely spread modes, in which case the minimization chooses to emulate a single mode. In this example, the modes are equal but in different places, so the divergence could equally have been minimized by choosing the one on the right side instead. In cases where multiple modes are not widely separated, the type of minimization on the right may still decide to blur modes together. Next, you could think about KL divergence as measuring the distance between distributions, so to speak, although this is an imperfect analogy because the function is asymmetric, as mentioned previously. But with this frame of mind, you could understand the cross entropy of two distributions as being that distance, as placing that distance in space. Here's what I mean. If you had 2 points in space, you could use a vector to describe the position of A relative to B. But with only that information, you don't actually know where they are in space, you just know where they are relative to each other. If you then have a vector describing where A is with respect to the origin, then having the different vector allows for placing both of the points in space, because you know the position of one with respect to the origin, and then the position of the other with respect to A. So in a manner of speaking, you could think of the cross entropy as having that position component added in, which is the Shannon entropy of the first argument. And as an aside, the authors note that when 0 log 0 is encountered, it is treated using a limit case as being equal to 0. The idea of structured probabilistic models is that you can have a system of many random variables where variables are related to one another. The authors note that often these distributions involve direct interactions between relatively few variables. In this scenario, using a single function to describe the entire joint probability distribution can be very inefficient, both computationally and statistically. A more efficient way to get the job done is to change the way that the overall joint distribution is represented. The beginnings of a structured probabilistic model lay in identifying the relationships between the constituent random variables in a system, such as dependencies and independencies. With those relationships in mind, you can mathematically split a probabilistic distribution into many more simple factors that are multiplied together. The result is computationally much more simple, making this a better method for machine learning applications, since so much computation is intrinsic to these methods. The factorization itself can be represented using graphs indicating the dependency relationships. The graphical representation itself is what we refer to when we say the structured probabilistic model. So again, graphs come in two forms, directed and undirected. In the context of probabilistic models, these mean different things, as noted on the right. It's best to see examples to make sense of this. In a directed probabilistic model, the direction of the arrows points to the dependence. The decomposed probabilistic model is represented as the product of a number of terms, with one for each random variable. The term for each variable is a conditional probability, which is conditional on the values of all those variables that it is dependent on. That can be seen in this example, where A is the only independent variable, so the probability term is not conditional for A. Following the graph from there, each random variable term is then represented by a conditional statement based on which arrows are pointing at it. The process for computing the joint probability using an undirected structure is notably different. First, variable cliques are identified. These are collections of variables where every variable in the collection is connected to every other one. As shown on the left, in this example the cliques are A, B, and C, B and D, and C and E. Each clique then has a function associated with it. The product of all these functions, for all the cliques, creates a function, in total, which is proportional to the probability of a collection of random variables values taking place, the joint probability we're interested in. The key word is proportional. This function, as is not a probability distribution, as it doesn't integrate to 1, among other things. So the inputs that yield higher values for this function are more likely input collections. If you consider z as the integral of this function over its domain, then dividing by z normalizes the function, such that it becomes a proper probability distribution that results in values between 0 and 1. Now I'll just mention again that either an undirected or directed graph approach can both be used to describe a probability distribution. They don't rule one another out. Furthermore, distributions themselves are not directed or undirected. Only the graphs describing them are. Finally, the authors note that these two methods are simply used as languages for describing probability distributions. No further understanding is necessary until the final section of the book, which discusses research topics that were pertinent at the time of publishing. This concludes the Chapter 3 summary for the Deep Learning book. In the next video, we're moving on to Chapter 4, which deals with computational methods. I hope that this has been helpful and informative. Thanks for watching and take care.